This is my showcase of low-level optimization. The first thing I did was changed the objects from being in a list to being in a vector because of linked lists. Well, lists in C++ are instantly initialized as a linked list, which are a lot slower to read from and take up a lot more memory space, and vectors just worked quicker and was more efficient for the program. It also then meant I had to change all the physics update loops to loop through a vector rather than an indexed list. I decided to tackle the time optimizations first rather than the memory ones. So I first added a 4-quadrant thread. Saw some obvious improvements, splitting it across 4 different thread areas, and I defined the regions as seen earlier in my forum thread. And from there, I input a user-requested number of regions. So currently this one is running in 8 regions. I also have a user input number of threads. This can be separate, so I can rerun the program with, say, 32 regions on 16 threads, and it will run now across 32 regions. I interpolate the color of the boxes across from left to right, so you can see it gets brighter on the right side and darker on the left side, to showcase each region. It's harder to see when there's more regions. It was easier with 8, but this worked as regioning. I saw obvious improvements. The amount of time the CPU actually spent calculating the check collision function reduced massively. So they optimized the program's efficiency quite a bit. I then added thread pooling, so creating all of the threads at runtime, well, on initialization when you input them in, and just holding them with a conditional variable that would alert when a task got added to a task vector. That would then awake the threads to keep looking at that task vector and yielding the main thread whilst it completed all of it, and then would go back to the main thread afterwards and render the screen. This meant that you didn't have to make the overheads. You didn't have the overheads at runtime of making however many threads. So in this one, it'd be 16 threads every single frame, which it sped up the program massively. In terms of FPS, I'm currently on a monitor that refreshes at 144. So if I display, not that button, if I display the FPS of the physics, it refreshes at roughly 144. If I were to add a lot of objects, it starts to show differences and changes in the FPS time. Still running at a decent pace, but certainly struggling more when you get more objects in. I can press 1 to add more objects at 100 at a time. I can press 2 to remove objects. And again, I can display the FPS and it goes back up. I then decided to look at memory. The first implementation I did was of a tracker. I added a header and a footer class. Each of them just hold an int currently. And there was then a global tracker that when you add objects, adds the size of the object you're adding to the tracker. So if I print out the tracker memory, this is currently what's been allocated throughout the program, and this is currently what has been destroyed throughout the program. Currently in use is here. I have the one for spheres with headers and footers, one for just spheres, one for just the boxes with the headers and footers, and then the globals. A couple different ones. If I click on objects, I can remove certain ones. So if I remove more boxes than I do spheres, and then I print out the memory information, you can see that boxes has a higher freed number than spheres. Shows that it's working. It has a general tracking system. If I hold 2 and the currently in use is 0, there is nothing actually on the objects. If I go up to a lot more, you can see that the dates actually increase and are tracking the memory correctly. If I then decided to do memory pooling, I will quickly reset the simulation because it's slowing down. I will run it with 8 regions on 8 threads. There is a memory pool initiated on runtime of 10,000 objects. There is a cap to how many you can spawn to 10,000, of which has just been hit. and it initiates them, and you see a massive performance increase. The heat allocations went down massively because there was nothing being generated at runtime. It wasn't force calling constructors, because of using malloc instead of new and defining like a new operator new to do this memory pooling. It allowed the objects just to spawn easier. There was less overhead process, and generally optimized it. The last check I did was I made a canary for a Stack Overflow, just to stop it from Stack Overflowing. The canary works by, it defines a local guard value and then a global guard value. It copies the global guard value into local when it's created, and then when the canary guard falls out of scope, so out of a function, it checks to see whether that has changed, and if it's changed, then something has Stack Overflowed into the local guard and changed what it is from the global, and therefore calls an abort saying this is broken. I have a function on 8 that force corrupts it. So if I press 8 now, it calls an abort, and it says stack canary check failed, and it failed at the function called canary demo, which is just what the function when I press 8 is called. And you can click abort and go through the stack to figure out where it's broken itself. That is my general program. It runs a maximum of 10,000 objects, as said. You can put in however many regions you like. I've stress tested it, and it can handle 256 regions on 128 threads for about 600 objects, and then it just completely aborts everything because there's too much memory being assigned. But it runs amazingly quicker than the original base framework, which you can see throughout my forum thread posts. And I chose to implement these ones because of it seemed, from my research, it showed that these would have big impacts in this specific situation. The entire situation of this project was just to spawn a lot of objects in one space, so regioning and memory pooling just seemed like better ones to do than some of the other optimization techniques out there because it applied to this scenario better. Space applies the force upwards. And that is my project. Thank you.